Today we will see some basic concepts about arches. Arches are used when beams are to be provided in large spans. If we are giving beams for large spans, it will be very uneconomical because self-weight will be large in those cases. So the self-weight of the beam itself contributes to the stress in large proportions. And so it is difficult to design beams for large spans. In such cases, it is better to provide arches. What are arches? Arches are nothing but curved beams that transfer loads to the plane. Arches transfer loads to abutments at the springing points. You can see abutments given on both the sides. The point from which the arch starts from the abutment is called the springing. Hinge may be provided at both the springing points. Springing point is the point, it is the starting point of the arch from the abutment. The topmost point of the arch is called the crown. You can see the crown here. The topmost part of the arch is called the crown. Sometimes a hinge may be provided at the crown also. Now, the height of the crown above the support level, that is called rise. Height of the crown above support level is called rise. Because of curved nature of arches, they develop horizontal forces. Let us see the internal forces in the arch. First one is normal thrust N. Second one, radial shear Q. Then bending moment M is also there. What are the different types of arches? Arches can be 3-hinged, 2-hinged or fixed arch. Different types of arches are there. Some types are shown here. 3-hinged means there are hinges provided at the springing points and at the crown. 2-hinged means hinges are provided at the springing points only. And fixed arch ends are fixed in nature. Before the starting the analysis of arches, we should have some idea about the elastic theory of arches. In the figure given, you can see an arch with loads, a system of loads W1, W2, W3, W4, etc. First, we will draw a vertical line in which vertical loads are drawn to some scale. This is the vertical line. W1, W2, W3, W4, etc. These loads are shown using the lengths A, B, C, D, D, E, etc. to some scale. Now we are going to select a point O outside the line. It can be selected anywhere. Now we will join OA, OB, OC, OD, OE, etc. Then in the arch, we will draw lines parallel to OA, OB, OC, etc. For example, line drawn parallel to OA is T1, line drawn parallel to OB is T2, likewise. Now, this particular figure, this is called a funicular polygon, which represents the forces. Okay, this is a funicular polygon, which represents the forces. A number of polygons are possible, as O can be chosen anywhere, at any distance and anywhere. Funicular polygon which lies within the actual arch is called line of thrust. That is, this line T1, T2, T3, T4, etc., T5. Funicular polygon which lies within the actual arch is called line of thrust. Polygonal arch following the path of compression is called theoretical arch or linear arch. That is, this line T1, T2, T3, T4, T5 is called line of thrust, linear arch or theoretical arch. Now we are going to the proof of Eddys theorem. Eddys theorem states that bending moment at any section of an arch is proportional to vertical intercept between linear arch and central line of actual arch. You can see the you can see the actual arch PQR here, PQR, okay. PQR is the actual arch. Now, PSTUVR is the funicular polygon representing the theoretical arch. Now, let us select a point A on the line of thrust or compression. It can be selected on any line of thrust. Now from A, let us draw a vertical line AB. B is a point on the actual arch. Okay. From A, we are dropping a perpendicular, we are drawing a vertical line towards the actual arch, which means set B. Now, you can see that N is inclined at an angle theta with the horizontal. So N is the normal thrust. N cos theta, this N cos theta is a horizontal component of N. Okay, so let us take moment about B, bending moment about B, that is equal to N cos theta into AB. N cos theta is constant throughout the arch. That means N cos theta into AB is the bending moment. So bending moment is proportional to AB. Therefore, bending moment is proportional to vertical intercept, and we have proved Eddys theorem. Bending moment at any section of an arch is proportional to vertical intercept between linear arch and center line of actual arch.